I think it is meant to be pronounced Bézier, but I'm not a French speaker, so I'm going to refer to it as Bezier. Okay, what we're going to be looking at today when we look at Bezier curves is essentially polynomials. You're all second year math students, you know what a polynomial is. But just to refresh your memory, this polynomial is a function which is defined by a sum of variables raised to powers and multiplied by coefficients. So a polynomial is simply a sum. So this is sort of the basic definition. So A are your coefficients, X is a variable, N is the power, and if we sum them, okay, we have a polynomial function. Okay, so A0 is just a constant, A1, that's a constant times X, which is our variable, plus A2 times X squared, plus A3 times X cubed, etc., etc. So you're quite familiar with polynomials. The degree, well, I actually tend to use order for this, but the degree seems to be, I did a little Wikipedia search, and degree seems to be the term preferred of a polynomial. Is the highest power. Okay, so for example, if your highest power of X is 3, then we have what we call a cubic polynomial of degree 3. Okay, so the degree is simply the highest power. And we give different names to them. So a linear polynomial function, highest power of X is 1. Quadratic, highest power of X is 2. Cubic is degree 3. Quartic, degree 4. Quintic, degree 5, etc. Okay, septic, not quite sure. Not up on my sort of Latin. Okay, so that's a polynomial function. These are what we're going to be dealing with. Okay, so we want to define a polynomial function which defines our Bezier curve. Okay. Important quality or property of polynomial functions is the higher the degree, the more changes of direction the graph of your polynomial can have. So we all know a linear polynomial doesn't change direction. The gradient or the slope is constant for all values of X. A quadratic, the shape of a cup or a cap, depending on the sign of the X squared term. Okay, so that has one change of direction. So it's got a negative gradient here, goes through 0 gradient, and then we have a positive gradient here. So that's changed direction once. Cubic can have 2 changes of direction. Quartic can have 3. Degree 5 can have 4, degree 6 can have 5, etc. So it's always the number of changes of direction is 1 minus the degree of that polynomial. Okay, so that's important to sort of realize, and when we look at higher order degree Bezier curves, you'll see why. Okay, so Bezier curves are expressed as parametric equations. So this is quite similar to how we express the vector equations. Okay, so we have some parameter. We usually use t to be our parameter, although that could be anything, could be arbitrary. And we define a point on our curve or on our function by this parameter value. Okay, so for example, t is my parameter. Let's say I have a line that goes with starting x coordinate x0 and finishing x coordinate x1. Okay, well, a point on the line corresponding to the parameter t can be expressed as 1 minus t times x0 plus t times x1. And similar for y. So this is what we call a parametric equation. T, the parameter, tells us what the values of x and y are. Okay, and this is the parametric equation of a straight line where x0, y0 is your start point, x1, y1 is your end point. So it's very similar. We could rearrange that to give us the vector equation of the straight line if we wanted to. We can generalize, well, we can group x and y into a single point P. So if P0 is x0, y0, and P1 is x1, y1, so for a given parameter value t, a point on the line between P0 and P1 is given as 1 minus t times P0 plus t times P1. Okay, that value of t is in the range 0 to 1. Okay, it can't be outside that range. When t is 0, okay, so here I've got my line from P0 to P1. When t is 0, this first coefficient, 1 minus t, will be 1. And the second term, t times P1, that will be 0. So I've just got 1 times P0. So therefore, when t is equal to 1, my point is at P0. If I increase t to be equal to a quarter, I'll have 3/4 times P0 plus a quarter times P1. So I'm now at this point. I'm actually a quarter of the way along this line. So if I go t is equal to a half, I'm halfway along the line, 3/4 of the way along the line. And when t is equal to 1, we have 0 times P0 and 1 times P1. So we must be at this point. So that value of the parameter tells us how far along this line our point P is. Okay, and that's essentially what we use to derive Bezier curves. So we use this parameter or parametric way of representing a straight line. Okay, so what is a Bezier curve? It's a parametric curve that is used to draw smooth lines. Okay, so far most of the graphics we've been looking at have all involved sort of polygons or straight lines. That's all very well and good, but the real world isn't all straight lines. So we need a method to draw smooth curves. And that's what Bezier curves give us. I always think this is a bit tight, really, but it's named after a guy called Pierre Bézier who worked for Renault, but he didn't actually think of it first. There was a guy working for Citroën called Paul de Castellau who thought of it first, but Bézier's claimed all the credit. So that happens quite a bit in mathematics. So if you do come up with a wonderful method, make sure you slap your name on it. Okay. Common applications, computer-aided design software. So it was originally designed for the car industry. So obviously you want cars to be sort of aesthetically pleasing or nice curves. And it's also used in 3D modeling and sort of most common in typefaces. Okay, we're looking at fonts on this screen. All these fonts are Bezier curves. Okay, so the B in Bézier, that's defined using Bezier curves. So whenever you use a word processing package or any form of text on screen, you're using Bezier curves. We've got Bezier curves are essentially polynomial functions. And if we have an n-degree Bezier curve, we need n plus 1 control points to define it. So a Bezier curve is defined by a number of control points. So if we have a quadratic curve, we need 3 points to define it. Translations, rotations, reflections, etc., can easily be applied to the control points. We don't have to apply it to all points on the curve. We can just apply it to the control points, and therefore you can draw the curve and you can apply those translations. You've actually used Bezier curves already in your assignments. That teapot, which you've been using for the hidden surface removal, that's drawn using Bezier curves. Okay, and we'll look at that on Friday. Here's an example of Bezier curves in action. This is a Times New Roman S. Basically what I did is I printed an S in very big font, and I sort of tried to determine where the control points were. Now this S, quite a number of Bezier curves have been put together to make that S. What you can see here is the red circles are what we call control points. So if we look at, there's a curve, that curve there is one Bezier curve. Okay, and that's defined by this point, that point there, in that point. So I've got a number of Bezier curves sort of stitched together, and that defines that S. What I've also done is, what I've done here is I translated all these control points so that the center of S is at 0, 0, and then I shrunk it. Okay, is it a factor of a half? Yes. So I shrunk it by a scale of a half. I translated it over here. That has been applied to the red points. Okay, then I just draw the blue line, which is our parametric polynomial function. So the S moved from there to there, just using our translation, rotation, scaling stuff, which we did in term 1. Okay, so that's how word processors sort of scale up your font. So if you choose a large font size, what it's doing is it's just scaling up the Bezier curves. Okay, so how do we define one, derive one? So what I'm going to do here is I'm going to have a look at the derivation of a quadratic Bezier. Now, quadratic, obviously, will have a polynomial of degree 2, and we need 3 control points to define a quadratic Bezier curve. So you need one more than the degree of the curve. So what I've got here is I call them P0, P1, and P2. These are my control points. And what we do is we use the parametric equation of a line to calculate the points Q0 and Q1. So Q0 is going to be somewhere between P0 and P1, and Q1 is going to be somewhere between P1 and P2. Okay. So the blue line represents is a straight line joining Q0 and Q1. This is for the parameter value 0. So when t is 0, Q0 is at P0, and Q1 is at P1. And I've also, it's quite hard to see here, but I've also put the point, which is on the line between Q0 and Q1. I marked it as a black circle. Okay, so if I increase the parameter value, so t is 0.1, okay, so Q has moved a bit along the line between P0 and P1, and Q1 has moved a bit further in the same distance from P1 to P2, and that black circle there has moved the same distance along Q0 to Q1. Okay, so if I move Q0 and Q1 a bit further, okay, and do it a couple more times. Okay, so what we see is as Q0 travels up between P0 and P1, so it's currently here, we do the same for Q1, and then this black circle is the same parameter value t, but between Q0 and Q1. So if I keep doing that, so I've got all my points. Okay, so that's just sort of moving. So for all my values of t, starting off at 0, okay, so this is t starting off at 0, then it's 0.1, then it's 0.2, 0.3, etc. Okay, so that's why I got you to draw that pattern when we first started. So these points, which I've shown with the black circles, they are on our Bezier curve. So what I can do is I can draw a curve through those points, and that's our curve. Okay, so that's our quadratic Bezier curve. Okay, so how do we derive the polynomial function? Well, if Q0 and Q1 are on the lines P0 to P1 and P1 to P2, if I use our parametric equation of a straight line, I could define Q0 and Q1. Now, what I'm going to use is I'm going to use CT as being the point on the Bezier curve corresponding to the parameter value t. And that's on the line between Q0 and Q1. So therefore, CT would equal 1 minus TQ0 plus TQ1. Well, Q0 and Q1 are given up here. So if I substitute these two into this equation, I get this. Okay, so this is a quadratic polynomial function of t. Okay, so I've got 1 minus t squared times p0 plus 2t, 1 minus t times p1 plus t squared p2. Okay, so that's my quadratic polynomial function, and that is my quadratic Bezier curve. Okay, that whole process is an example of what we call de Castiglio's algorithm. What we could do is we can start generalizing that. So we don't just want to work with quadratic Bezier curves. We want to work with perhaps higher orders. So de Castiglio sort of generalized it. So what we're going to do is let Pij denote the control points. When j is 0, we've got our initial control points. So those are our P1, P0, P1, P2. Okay, so when we have P10, we're at P0. Sorry, P00, we're at P0. P10, we're at P1. P20, we're at P2. When j is 1, we're at the Q points. And when j is 2, we're at the point on our Bezier curve. So the j sort of gives us what I tend to refer to them as levels. Okay, so when j is equal to the degree of the Bezier curve, that's the point on the curve. When j equals 0, you're at the control point. Okay, so for in general terms, the value Pij is equal to 1 minus t times p, and we subtract 1 from j, plus t, we add 1 to I, and subtract 1 from j. Okay, this is exactly the same as what we've done here. Oops. Exactly the same as this. It's just sort of written in a more generalized way. De Castiglia actually presented it in this manner, which is sort of easier to understand. Okay, a value of a point Pij is a combination of this point, the coordinates at this point, and the coordinate at that point. Okay, so the horizontal arrow denotes the 1 minus t coefficient. The diagonal arrow denotes the t coefficient. So it'll be 1 minus t times that coordinate, or that point, plus t times that point. So if that's P0, that's P1, that'll be Q0. Okay, so that's the same diagram, but this time I've written it in using those subscripts. So the red P points are your initial control points. Your blues, okay, notice that J is 1 in this case. Those are your Qs. And the point on the Bezier is P02. Okay, we can extend that. We can extend that to cubic Beziers. Okay, cubic Bezier is degree 3, so we need 4 control points. Okay, so here, if we have a look at, we've got P00, P10, P20, P30. Those are our 4 control points. So if we've got 4 control points at level 0, when j is 0, we have 3 at level 1. So the blue one's here. So that's, if I go back to our P and Q, that's Q0, Q1, Q2, but obviously we're using subscript notation. Okay, so P01, P11, P21. Okay, so we've now got 2 blue lines, so we're going to have 2 points at the next level. Okay, so we've got P02 and P12. So we've only got 1 green line, so if I go partway between those 2, I'm at the point on the Bezier curve at P03. Okay, so if I sort of, whatever our parameter value t is, that'll give me a point on this black curve, and that's our cubic Bezier. Okay, well, if you sort of derive a few of these sort of quadratic, cubic, quartic, etc., you start to see a pattern. And the pattern was known by a guy called Bernstein. We can write our general form of an n-degree Bezier curve as this summation. So Pi is your control point, so P0, P1, P2, etc. You need 1 more control point than the degree of your curve. Bin, these are what we know as Bernstein polynomials, and they're defined like so. Okay, this n over I, that's not a matrix. That's what we call the binomial coefficient. Some people write it as NCI, sort of n choose I. So that's the binomial coefficient. Okay, so let's say we've got a quadratic. N would be 2. I goes from 0 to 2, so I've got 3 terms. So I've got B02, B12, and B22. So for whatever I've got here, whatever the value of n is, so if it's a quadratic, n would be 2, and I would go from 0 to 2. And that gives you what we call Bernstein polynomials. Okay, binomial coefficient, just to sort of recap your memory. It's a number of ways of choosing I items from a set of n items. Okay, and we can calculate it. You're up on your probability theory using factorial notation. The good news is Bernstein Bezier curves we only end at usually sort of quite small degrees, so less than maybe 4 or 5. So the way I tend to think about it is use Pascal's triangle. Okay, so you're familiar with Pascal's triangle? Sort of start with 1 at the top, so down sort of the edges we have 1s, and any number is the sum of the 2 numbers above it. So that 2 is the sum of those 2 1s, that 3 is that 1 plus 2, etc. These give us our binomial coefficient. So for example, when n is 3, 3 choose 1 is 1, sorry, 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. Okay, so that's your binomial coefficient. So if we want to derive a cubic Bezier curve, okay, n would be 3, and we'd need 4 Bernstein polynomials. I is 1, 2, 3, 0, 1, 2, 3. So when I is 0, we have 3 choose 0, which is 1, t to the power 0, which is also 1, 1 minus t to the power 3. That gives us 1 minus t to the power 3. When I is 1, we have 3 choose 1, which is 3, t to the power 1, multiplied by 1 minus t to the power 2. And we can calculate the others in a similar way. So these are our Bernstein polynomials. Okay, quite easy to calculate. They're just something times t times some 1 minus t to a power something. Okay, well, how do these behave? Well, this is the quadratic Bernstein polynomial. So these are the 3 polynomials which define a quadratic Bezier. The horizontal axis here is t. Okay, so t goes between 0 to 1. And the Bernstein polynomial also goes between 0 to 1. Okay, so when t is 0, what this means is we have 1 times our first control point plus 0 times our second control point plus 0 times our third control point. So when t is 0, our Bezier curve is at the first control point. Let's have a look at when t is at point 2. Okay, so if we have a look at the blue line, okay, we have about 0.65 times our first control point, about 0.35 times our second control point, and a little bit times our third control point. So as t gets bigger, the amount of sort of influence but our first control point, our first Bernstein polynomial has on our curve is reducing. And the amount of influence that our second control point has is increasing. So when we're in the middle, when t is a half, we can see that it's the second control point which has more effect on the position on the Bezier curve. And as t gets towards 1, we can see that it's the last control point that has more of an effect, and the other 2 have less of an effect. So that's what's happening. That's a quadratic behavior. That's a quadratic Bernstein polynomials. I've also graphed it for a cubic. So in cubic, you have 4 control points. As you can see, when t is 0, it's only the first control point that has an effect. As t increases, the amount of effect that the first control point has decreases, and the others increase. Okay. And likewise, when t is close to 1, it's only the last control point that has an effect. Okay, like with many things in graphics, it's often convenient to actually express Bezier curves in matrix form. Okay, so we need to calculate what the Bernstein polynomials are, but we can do that beforehand, before we have to calculate any coordinates. So what we have is we have a matrix equation where we have a matrix of our control points, P0, P1, etc. These will all be column vectors of coordinates. Okay, so if you've got a degree n, well, you should have n plus 1 control points. M is a matrix which will depend on what degree Bezier curve you have. And T is a matrix of parameter values. So T to the power n, T to the power n minus 1. We reduce the power until you get down to 1 at the end, T to the power 0. Okay, so what we need to do is calculate or derive what that matrix M is. Okay, so if we go back to the quadratic Bezier curve, okay, what I've done here is I've just expanded out the brackets, okay, and I've kept them into the factors of P0, P1, and P2. Okay, so if I expand out the brackets, this is T minus 1 squared, 1 minus T squared. This is 2T times 1 minus T, and that's just T squared. Okay, so what we have is T squared minus 2T plus 1. So our top row is 1, minus 2, and 1. So if we multiply those two, or the second and third matrix together, okay, we'll get that. Okay, second row is minus 2t squared plus 2t. And the third row is just 1 times t squared. So that matrix is the same for all quadratic Beziers. Okay. We change the control points. Okay, we don't change that matrix, and the parameter values can change, but we just define them to be somewhere in the range 0 to 1. And if we do the same for cubic Bezier curve, we have this. Okay, so do exactly the same, expand out the brackets. 1 minus t cubed is minus t cubed plus 3t squared minus 3t plus 1, sorry. Okay, so all we need are our control points, multiply it by, or calculate whatever this matrix equation is, and we've got our point on the Bezier curve. Okay, we're going to have a look at a example in a minute, worked example. Few properties of Bezier curves. They always begin at your first control point and end at your last control point. So we know they're going to pass through those 2 points. A Bezier curve can be a straight line, but only if you can draw a straight line through all your control points. So sometimes you do need to define straight lines. And all we do is make sure the control points line up. The start and end of a Bezier curve is tangential to the start and end section of control polygon. So what I mean by that is this gradient here between P0 and P1 is the same as the tangent of the Bezier curve at that point. We can divide Bezier curves. We can split them up into 2 Bezier curves and keep doing that if we want. And a Bezier curve is always contained within its control polygon. So if I was to draw a polygon around the control points, our Bezier curve is always always contained within that polygon. Okay, here's a few examples. In practice, we only ever really use cubic Bezier curves. Okay, reason being is they're easy to calculate. If we want a complicated sort of swirly pattern, we just put a load of them together. Okay, so these are a few examples of cubic Bezier, and you can see that the control points sort of determine the shape of the curve. Okay, so there's a standard one. If I want it to loop round a bit, I just move the second and third control point out a bit. You can actually perform a loop. Okay, so that's your first control point there. This is the second one. That's the third one, and that's the final one. So you can actually sort of loop them, sort of make a twist. You can also make a couple of turns in it. Because this is a cubic, it can have 2 changes of direction. So first control point, second, third, and fourth. So you can draw sort of swirly patterns and things like that. Okay, another example. Okay, what you've got to do for assignment 11. Okay, so for assignment 11, you've got to write a MATLAB program which can calculate the Bezier curve using some control points and draw the MMU logo. Okay, so for the sort of the basic part, okay, you can draw this, and I've called it an arrowhead because it kind of looks like an arrowhead. This is made up of 8 curves. Okay, there's one starting there and ending around about there, another starting where that one left off and ending there, and the same the other side, and 4 in the middle. Okay, if you notice, it's got a symmetry about the central, about the line through the center, so you only actually have to define 4 curves. Okay, one go from there to there and there to there. Once you know that one, just the other one's symmetrical. This is going to take a bit of trial and error. I mean, when I drew this, I sort of moved the control point a bit, tested it. Is that right? No, let's move it slightly more. Is that right? So it's a little bit of a trial and error process. But eventually, I mean, this took me 20 minutes to do. Okay, just to do that one. Shouldn't take you long. So you're going to have to, what I'd recommend you do is write a function, but given 4 control points, can output the coordinates of that curve. Okay, so that's the first bit. That's why I call the basic bit. Once you've got one arrowhead, what you can do is you can copy it, translate and rotate it. Okay, so all I did was define that once, and then I translated it and rotated it and put them all together. Okay, so there's the top one is sort of all I've done there is moved it. I didn't have to rotate it. Okay, this one here, I had to sort of rotate it a bit and move it into position. Again, a little bit trial and error. Okay, so that gives you that one. And if you want to be really fancy, you use the fill command to fill them all in. Okay, so you can see we could use Bezier curves to do a bit of graphic design. Okay, in the notes, if I could just find it. I don't even know where it is. Aha. I've given you a massive hint in the notes on page 137. Okay, here's the function for a quadratic Bezier. Essentially, take that, define M to be your 4x4 matrix, T, okay, just add another row to it for T cubed. That's the same. Okay, essentially, that's a quadratic Bezier, very, very similar for a cubic Bezier. Okay, so that's a function. So that outputs C, which are your coordinates on your Bezier curve. P is your control points, and T is parameter. Okay, and this one down here actually uses that to draw. Okay, so define your control points, generate parameter values. So they're in the range 0 to 1, and I just used a small increment. Calculate your Bezier curve and then plot it. Okay, you're going to have several put together to actually draw the arrowhead. Okay, so you're going to have to put. Okay, so you're going to have to call this quadratic or your cubic Bezier a number of times. Okay, that essentially that code there at the top of page 137 is what you have to alter. Okay, what I'm just about to do, I just stop the recording. Right, if you flip